Colleagues, nice to see you here in the Technology and Innovation Centre, and a very warm welcome to our colleagues that have joined us online as well. My name is Jim McDonald. I'm the Vice-Chancellor or Principal of the University of Strathclyde, and it's a very warm welcome here to the Technology and Innovation Centre here at the University of Strathclyde. TIC, as we refer to it as, has been the kernel of the creation of Scotland's first innovation district, and it's it has many clones now that are appearing across the industrial and academic landscape. So the Glasgow City Innovation District you're sitting in is now building quite a lot of momentum around key clusters, one of which is quantum, but we also have 5G capability here, medtech, fintech, space and industrial informatics, low carbon technologies all the way through to pharmaceutical manufacturing. So today what we're talking about around quantum fits very nicely with what many of my colleagues, many of whom are represented in the room today, are working on, building on the fantastic photonics capability that sits in this part of the world anyway, across Glasgow and Edinburgh and beyond. And that's clearly the, shall we say, the foothills of building that quantum capability. Of course, we are hosted by the Foundation for Science and Technology. Gavin, very welcome to you and the team. And for those of you in the room, we'll talk a little bit about how you pose questions. And for those online, I'll tell you in a moment how you participate, and we would welcome that, of course. Very big thanks to the Royal Academy of Engineering. I've had the privilege of being president of the Royal Academy of Engineering for the past 5 years, and it's good to see them investing and supporting events such as this. And we'll hear from the author of, the person that chaired the latest piece of work from the Royal Academy around the quantum infrastructure, which we hope is going to influence policy as well as bring together the academic and the industrial and the investor community over the next few years. Strategy, of course, is one thing, but delivery is even better. And engineers are around for trying to get things done and finding solutions, and we might actually touch on that today as well. And as many of you know, there's a lot going on in this arena, and the timing is very good. And I know FST were keen, alongside the Royal Academies, to bring together the community that we have represented today to discuss where we are and what the potential is going forward. The UK undoubtedly has enormous capability in quantum technologies, not least of which in the academic arena. But we're seeing now a growth in startup companies. We're also seeing very large corporates. They're not just exploring now, but implementing quantum solutions to what they might require, whether it's in sensing, whether it's in other applications, from everything from manufacturing through to defence and security. And it's been clear to me, as I've spoken to my own colleagues in quantum technology, the physics, the maths, the advanced materials that sit behind all of this, we're starting to see, I'm happy to say, a convergence with the engineering community as well, because we need to make things and we need to find devices and support their applications. And as I mentioned, the Royal Academy of Engineering, you'll have seen on your seats the copies of the report around quantum infrastructure. I commend it to you. For those of you online who don't have the physical copy that those in the room have, then you can certainly find that report on the Royal Academy of Engineering's website. And please have a look at it, because as I was just speaking to Francis about there, this is an amalgam of the voices of the community, whether it's in startup, spin-out, industrial or academic, or indeed those in the policy arena. And we know that the level of application is growing all the time, but the key thing here is now, how do we take that scientific understanding, the potential engineering of solutions, and work with UK government and Scottish government? And certainly we have colleagues represented from Scottish government here today and from the UK system. Where do we go from here? Because the last UK government did make a major commitment, identifying quantum as a critical technology for the UK. We've yet to hear. I suspect Mr. Starmer's not talking about quantum technology this afternoon. We never know. But certainly as we see DCIT building forward, as we say, and I roundly welcome the appointment of Lord Patrick Vallance as the Minister of Science. He understands the academic community, but he understands how to translate research, innovation into economic and social impact. So we're at an important flex point, as it were, in government, and let's hope quantum figures prominently in how we build this capability around the science and research base. And to explore these issues, I'm delighted to say we have 4 outstanding speakers. I'll introduce the first just in a moment. After the four speakers have given their presentations, then we'll convene a panel session. We have two of our speakers online, and we have Francis and Simon here with us in the room. But as we go, please, for those of you online, you'll see online in your screens the website Slido. Enter the meeting number, #3344213, and then type your question, and Gavin will be assisting me just to keep an eye on the questions that are coming in to make sure that those outside the room get a chance to pose questions just as those of you in the room shall. So do your questioning online at any time, and we'll make sure that's played into the Q&A session. So, without any further delay, it's a real pleasure for me to introduce Dame Frances Saunders. And Frances was the chair of the Royal Academy of Engineering's Quantum Infrastructure Review for 2024. Frances spent most of her career in a series of research and science and technology management roles within the civil service, in the MOD and in BASE, now DCIT, where she was responsible for the interface with the research councils, enormously important. Her final role was as chief executive of DSTL, where she held that role from 2006 until she retired in 2012. And she now undertakes a portfolio of voluntary advisory work and remains a great supporter of the Royal Academy of Engineering, I'm happy to say, in areas of science and engineering in a number of areas, of course, including quantum. So, colleagues, if you allow me to introduce Frances, and please welcome her to the podium. Thank you.
Well, thank you very much for that very kind introduction. And it's a real pleasure to be here, and with any luck, is it the middle one or the... There we go. I'm going to have a short introduction to where we are with quantum, and then look particularly at the infrastructure review, which you now have a copy of, in terms of, well, what can the infrastructure do to help the next phase of the development of quantum technologies and the movement from, as Gavin said, sort of research to reality. So where are we now with quantum? And I would probably find most of you in this room actually are very well aware where we are. We've had 10 years of the National Quantum Technology Programme, 2 phases of the current hubs, covering everything from quantum computing, quantum sensing, quantum communications, and so on. And the thing that I think I'm most proud of for the hubs is the way they've managed to get technologies out of the lab towards the hands of users. If you'd asked me 10 years ago, would I have expected to see cold atoms on ships and trains and on vehicles, I would have said, no way. But that's the sort of level of demonstration we're now getting. We're getting these technologies out of the lab, and that's an amazingly good result. The hubs have proven to be quite a good model, I think, for getting industry engagement. And actually industry engagement with support and funding from organisations within UKRI, like Innovate UK and so on, but nevertheless a large number of industry engagement. And we're seeing a number also of very good training opportunities for people in applied research, so not just doing PhDs in sort of fundamental physics, but actually looking at PhDs based on the application of quantum technologies. And those people are going out into the workplace, and some of the hubs are keeping tabs on where they're going, and a large number of them are either going into academic appointments in engineering departments or into industry itself. So we're seeing that beginnings of the higher level appointments of skills that the quantum ecosystem will need if it's to be successful going forward. The other thing I think the hubs have done has strengthened the alignment within the academic community, bringing together universities with different skill sets, different abilities, different regions, has actually proven with alignment of funding to be a very successful model. So what we're going to do now is throw it all up in the air and see how the pieces come down into the new hubs that will be starting soon after the end of November. It's good to see that all those new hubs also have a strong level of industry engagement and industry commitment to supporting the training of PhD students and the like. So that I think is a good story for where we are with respect to the hubs. We've also had a commitment from government through its quantum technology strategy and the missions that they've launched. But of course, we have to remember that was the last government, and we need to see how much of that gets picked up by the new government. And I doubt, as you say, I doubt whether Sakir will actually be talking about quantum hubs this afternoon. The other point I wanted to make really was we are not alone. I think there was a lot of skepticism to some extent about whether quantum technologies were going to get there. I think that skepticism is reducing in a number of areas, so everybody wants to pile in. And there's a lot of money going into quantum around the world. And we need to make sure that we continue to accelerate the benefits that we can see from the investment we've made over the past 10 years. So I wanted to say a little bit about what I see as the challenge of translational research from the academic community into industry. Now, I'm sure everybody here is quite familiar with the idea of technology readiness levels, because they've been around for a long time. This should actually be a 3D diagram, because I think there's an application in systems maturity, which I'm showing up the top, but there's also manufacturability, which I would see sort of kind of coming out of the screen. And it's a very important sort of thing to think of as a team game, where we've got the universities, very good at discovery research and lab-based technical demonstrations. We've got industry who want products. They want manufacturable things that they can make money from. And there's often a gap in the middle. Now, the hubs, I think, have been quite good at doing this proof of concept demonstration and starting to look at the sort of technology development that's necessary on its trajectory towards products and services. But there's always a gap. And you need to kind of be going around this loop of analysis that says, is this technology ready yet? Is it good enough for this application? Can I make it? Can I make it cost effectively at high yield into a product that anybody might want to buy? And a lot of this is about reducing risk, whether it's the technology risk or it's the manufacturability risks. And this bit in the middle is where it can all go horribly wrong. And often does, and I've got lots of examples in my background of where things have gone horribly wrong. Because you can't throw this ball over the fence and assume that from university to industry, somebody will pick it up. You have to work together in this gap. You have to look at working as a team. Now, sometimes that gap's a bit too big for a university department to talk to a big company. And I think, I was visiting Fraunhofer today. Organisations in what I would consider to be the third tier, people who are interesting, they're like Janus, they can look both ways. They can look into industry and understand the language of industry, they can look into academia and understand that language, and they can problem solve, and they can help close that gap. So let's talk a little bit about the gap for quantum. I think we have to keep continuing the opportunities for this joint working. There has been progress made, but I do think there is a role for third-tier organisations to help facilitate that. We must speed up the iteration around this loop that takes it from an exciting-looking technology to something that somebody might want to buy. And you have to do that a number of times, I think, to reduce the risk. So how can we speed that up? Making sure that we understand the difference between performance and effectiveness, and we understand risk and cost. Prototyping is a particularly important part for a lot of quantum technologies. And I say quantum technologies because, as we found when talking to people, QT, something people think it's a technology. It's not. Quantum technology is really about how we harness the quantum effects using a range of technologies. And we need to do prototyping. But that prototyping needs to be done in a way that industry can see that they might be able to pick it up at the end and continue to develop it with capabilities that they think that they could buy off the shelf, perhaps. Real-world experiments and trials are going to continue to be a very important part. It's about how we build confidence that we can not just get things out of the lab, but keep them running out of the lab reliably. And testing and evaluation, I think, will become an important part of that in this next phase. The second second point I was wanting to talk about was really about coordination. The quantum landscape, I think, is getting more complicated. There's just more moving parts. Actually, reorganising the hubs will change that landscape. There's more people entering it. There's more institutions in that space. So if you're a little SME, and maybe Simon will talk about this, how on earth do you find your way through that landscape? So is there more we need to do to signpost to people where the expertise lies? Who do they go to if they've got a problem? How do they actually start to move that technology on? And another part of that is how you facilitate access. Is there more we need to do to facilitate access to prototyping, facilitate access to skills? So for me, that improvement in coordination is also something we picked up in the infrastructure report. I've just put up this picture, it's in the report. As I said, the quantum landscape is really quite complicated. You might have all the great science and technology at the center of this diagram, but as you go out, you sort of pick up challenges, you pick up things that you want to sort out. And the yellow layer is where the infrastructure report has focused. Where are the areas which, if you like, are gaps in our ability to move from great science into real applications and real world? And those are the areas that we've said we thought might be worthy of consideration for additional investment. And I'll just go through these. As I said, we've got more detail in the report. But how do you start to move down that journey of being able to design the sorts of components and subsystems that are necessary to bring together and integrate to develop a quantum-based system? It needs to be made more cost-effective for people to get on that journey. Design tools can be an important first step. It becomes an even more important first step if those design tools are in some way integrated with the development of the prototyping fabrication capabilities that we need, so it becomes more seamless. We've talked about in the report the need for open access facilities to be truly open access. Costs of accessing some of these fabrication facilities can be something that puts off small companies. So is there more we should be doing to make those truly open access? And do we need to do still more to reduce the gap between the sorts of things that are very good for one-off or a few-off within a university environment to bring confidence that actually you could make these things in manufacturable real-world facilities out in industry? So is there a gap there that needs to be filled? Which takes us on to this whole area of advanced manufacturing. We've got quite a good set of capabilities for advanced manufacturing in the UK, but a lot of them have been built up around other application areas like telecommunications. The requirements of quantum are different, and people need to understand if those technology challenges for quantum mean that the current level of capability we have in manufacturing just isn't going to cut it. And so there needs to be an honest discussion about whether or not our current capabilities in manufacturing can be evolved into something that is of value for quantum. And we need to think about how we support industry in doing that. One of the other topics that came up, and actually we had a bit of a pushback on, was the whole issue of packaging and heterogeneous integration. A lot of people's view was packaging is just something industry does. And actually for quantum, when you're going to have to pull together lots of different technologies, reduce the level of losses, reduce noise, then heterogeneous integration may be the only way you're going to get to the size, weight, and power capabilities that industry is going to find attractive. Now, there's going to be a lot of things that you could do. You could invest in compound semiconductors. You could invest in silicon photonics. You could invest in heterogeneous integration and so on. These are not easy choices, and we didn't try in the report to place our bets, but it's worthy of additional discussion about where are those opportunities that would be synergistic with UK skills, where there might be opportunities for the UK to actually take a leading position, or certainly, if not world leading, then world competitive. So I will now just leave it really with a view on the review itself. It's always a challenge to bring together a group of people from very different backgrounds and get them to think about something that is of common interest. And the team at the Academy did a lot of consultation with small companies, large companies, academia, and so on. And we've done the best we can of pulling together this story. But what we need, I think, from this audience and from other audiences is continuing engagement to really understand what would be the best option for the UK right now. We say in the report, the very least we can do is to make sure our capabilities in design, in fabrication, in integration keep up with the pack. But there may be an opportunity to pick one of those and really turn it into a world-leading capability for the UK. So we'd be interested in your views, and we want to have a continuing discussion and dialogue with the community on the role that infrastructure could make in making sure that quantum technologies really deliver their promise. Thank you very much.
Thank you, Francis. And our next presenter will be online, and I'm delighted to introduce Professor Melissa Mather, Melissa is Professor of Quantum Sensing and Engineering and a Royal Academy of Engineering Chair in Emerging Technologies at the University of Nottingham. I had the pleasure of being chair of the Academy's research committee when these chair models actually came into being, and they support world-leading academics, and that trips off the tongue, but we invested, and along with others, for 10-year programmes of work, and Melissa's involved in just that, focused on developing integrated diamond photonic platforms for the next generation of quantum sensors. And the aim is to move existing quantum sensing instrumentation from complex assemblies to integrated devices suitable for adoption by non-specialists across a range of sectors. So very much resonant with what we've heard from Francis. Melissa is also seconded to the Government Office for Science within the Emerging Technologies team as a quantum specialist. So join me, please, and welcome Melissa to the screen.
Thank you very much. And can you can hear me and see me? I hope so. So apologies for not being there. I've had a bit of a bad dose of COVID, so best not to share it around. So I wanted to give academics viewpoint on where we are, particularly focused on quantum sensing, because that's an area that I'm working in. Yeah, again, it's a real privilege to be able to speak to you, and it's even a particular privilege to have funding from the Royal Academy of Engineering. And I think that's a key message. I want to probably echo the sentiments that have already been said today, in that this challenge is something for many communities to investigate. And with that in mind, I wanted to take you back in history and think about who was involved in quantum technologies back, I guess, in the early 20th century. This may be a photo that many of you know. I know as a teenager, I had this on my bedroom wall, which perhaps I was destined to work in this area. And this is the picture from the fifth conference of famous physics conference series. And if we think about in 1927, when this was taken, there were some really positions in quantum physics and theory that had been made. And even a quote from Heisenberg from this meeting was that it says that this conference has contributed extraordinarily to the clarification of the physical foundations of quantum theory. It forms, so to speak, the outward completion of quantum theory. So it's just a point of saying that back in 1927, there was this thought that quantum theory was somewhat complete. We had major discoveries at that point. And I think the fact that we're still today in 2024 talking about quantum technologies and quantum physics suggests that we're still very much on a journey. And I think that journey is really taking what these pioneering minds had and delivering it from the research to the reality. This is another photo. This was taken in 1981 in Boston, and in fact, it's the sort of the first conference that's sort of noted that combined physics and computer science. So to us now, it may seem unusual that physics and computer science were very separate disciplines, but this was really a pivotal moment where physicists and computer sciences joined together. And it was at this time when Richard Feynman said, you know, nature isn't classical. And if you want a simulation, you better make it quantum mechanical. And this was sort of arguably the birthplace of physics and quantum computing. So I think the main point here is that the seeds were planted back here, but what we needed interdisciplinary working, even at this early point. And if we look, I picked some more recent pictures. So this is from last year. This is from a conference on quantum sensing and metrology held in India, and the topics of discussion at this were actually curriculum development. So we're reaching a point where people are talking about quantum technology as curriculum, not just quantum physics or quantum mechanics, and showing that to lay a strong foundation of advancements in quantum sensing and metrology, and we need professionals from all fields to be contributing. And then to show you more in the photo gallery is the Gordon conference series last year on quantum biology. I mean, I think quantum biology is something that's been known for quite some time, but having technology, sensors, and instruments to actually demonstrate this is something where we're really coming to a point where we can start to, we can start to detect things such as tunneling, quantum tunneling in enzymatic catalysis, and we're looking more at magnetoreception, unraveling the mechanisms behind that, understanding how quantum coherence might play a part in photosynthesis. So it's the real, I guess, takeaway is that the growing importance of quantum biology, and at this time we're now developing quantum technologies that can help us uncover these aspects. And I had the pleasure to be at the Quantum World Congress a few weeks ago in Washington, and on the stage here is Johan de Silva from the Office for Quantum, and this was a whole session dedicated to international partnerships and talking about policy. And so the point is we're at a position, as I think Francis was looking at, is this is an international challenge. We not only need to look internally into the UK where we can have strategic advantage, but we need to look at ways we can scale the commercialization opportunities. We can think about responsible deployment of some of these technologies, and looking at how international partnerships will be really key to us getting the full potential of quantum technologies. So if we reflect on it, we've gone from probably the world's best minds in physics and chemistry, and we're moving towards where we're in a position where we're now talking about international policy and trade. So I think although it is an evolving space, it perhaps is representative of the complicated landscape that Francis was talking about. I then just wanted to, I mean, I think people in the room probably and online will know this, but the UK, we're very fortunate in having such tremendous strengths in quantum sensing, both in the research domain and in development, as Francis was saying. I think it's clear to say that the UK is at the forefront of quantum sensing research. And here's an example from the University of Glasgow, with their WeG, which is a major breakthrough in quantum gravimetry, harnessing these compact size portable devices, which are going to have applications in civil engineering, environmental engineering, and much more. And so I think the key takeaway here is that this just sort of exemplifies the world-class applications, and the commitment to addressing real challenges, taking things from research to reality. And I think I've said before, I think Scotland could be a quantum country in its own right. All the way across. I mean, this here is another great example of the sort of SPAD camera that's been developed jointly with University of Glasgow and Heriot-Watt, and by harnessing the power of single photon avalanche diodes, so SPADs, you've got this camera which captures light at extremely low light conditions, and you can see the unseen by sort of seeing obscured objects, and this has potential to transform things such as vehicles navigating and challenging situations, people trying to locate things in disaster zones, just as an example, and this is a significant technology step forward that's been showcased. If you come a bit further south, then the University of Birmingham have been working in the area of gravimetry and have spun out this company Delta G, and they've been using atom interferometry to enable measurements which are going to have real impact on looking at hidden infrastructure in civil engineering applications, looking at potentially groundwater levels, and indeed in general exploration under the ground. So this is, as I think as Francis says, it's probably 10 years ago we find this not something we would anticipate as being reality, but we're now in a position where you can have these types of quantum sensors out and about. Another example is the National Physical Laboratory are looking at sort of RF electric field probes. I guess MPL have got a massive whole sort of set of resources dedicated to quantum technologies, and I think as well as having quantum devices, I think the UK will be in a great position to be able to offer calibration services and setting the standard for quality products. And I think you can't look much further than NPL for having some history with that. Closer to where I am is at the University of Nottingham, where there are optically pumped magnetometers which are able to map the very weak magnetic fields in the brain. And so this is overcoming the use of cryogenic based squid magnetometers and enabling people perhaps to actually move about whilst they're being studied, and this will have benefits particularly for younger people who would find confinement to these sort of squid-based systems quite challenging. Another example is from Imperial College London and the spin-out company there, Digistain. Here they actually have applied the approach of undetected photons, I guess employing quantum entanglement to look at how they can detect the interaction of light with, in this case, tissue samples, but they can have the light being at a much longer wavelength than standard cameras and optics would allow through entanglement with a visible photon. And this system is actually being able to provide some objective measures and helping to stratify the type of cancer treatment for people. In this case, they've been focusing on breast cancer. And so that I guess showcases some of the big outputs that have come already. But I think what we need to do to accelerate this even further is that although the quantum landscape is brimming with potential, it can't exist in isolation. And to realize the transformative impact, we need to embrace adjacent technologies. And I think this is, a point that's been made already today. But I think we need to look at areas of, for example, of like precision manufacturing. So quantum devices have, intricate architectures and nanoscale components. So we need to be looking at, the demand and capability for having manufacturing at this level. Packaging of electronics, and again, the heterogeneous integration of components is going to be really key. I also often think with many of the quantum technologies, at some point we're trying to interchange between a photon or an electron or the other way around. So having the capabilities and skills for that will be quite important. I think the other thing is about building a quantum ready workforce. I think for this, we need a holistic approach. I think, we're fortunate that there are, young people who are interested in becoming scientists and engineers and working in technology. And we can see that university curriculum is expanding to incorporate quantum technologies beyond just a physics degree, for example. And we have got CDTs, which are giving us the PhD ready people. But I think we need a more holistic approach in thinking that, well, there are already people in the workforce who have got the capabilities or almost the capabilities we would need. So I think there are very many transferable skills that we could look at to efficiently develop a workforce in the short term. I think we also need to consider the skills at all levels of technical and PhD level. And I guess just my final point is that we're at a precipice, I guess, of quantum technologies and how they're going to impact the next generation of technologies. So I think what we need to look for is collaborations and together, I guess, working together to embrace the quantum challenge. And with that, I'll end.
Thank you, Melissa. NPL was mentioned. Strathclyde and Surrey are the strategic partners of NPL. In the building, you can see just out the corner here over the John Anderson building, there's a node of the National Timing Centre. We have an atomic or quantum clock that's been commissioned over there, which again is part of that overarching application of quantum technology to a national capability. Our next speaker is back in the room with us, and I'm delighted to welcome Simon Andrews. Simon is the Executive Director of Fraunhofer UK Research Limited, which operates UK's first Fraunhofer Centre, the Fraunhofer Centre for Applied Photonics, or CAP, that's based here in this building. It works in very close partnership with Strathclyde, but many other universities across the system, and is based here at the Technology and Innovation Centre. Simon spent 12 years in the medical device industry. He later worked here in Strathclyde at the Institute of Photonics for 7 years, and then was part of the team that established CAP in 2012. He's also chair of ERTO, which is the UK's Association for Research and Technology Organisations, and has several other board roles, including Technology Scotland, the Glasgow Science Centre, and the UK's Photonics Leadership Group, and exists right in that space between government policy, industry and academia. Simon, very welcome, and thanks for joining us.
Thanks very much, Sir Jim, and I can extend my own welcome to you, because this Technology and Innovation Centre here in Glasgow City Innovation District is the home of Fraunhofer UK and Fraunhofer Centre for Applied Photonics. So welcome to you all in the room, and welcome online. When mathematics becomes real, we call it physics, and when physics becomes useful, we call it engineering. And when engineering becomes successful, we call it manufacturing. And I love the framing of quantum technologies from research to reality, because quantum is such an overused, highly used, hyped word just now. All that noise tells us that there's a huge opportunity, but there's also a lot more to be done, because when quantum's truly successful, we won't even call it quantum anymore. We're beginning to explore a new level of nature of entanglement and superposition, all these amazing effects, manipulating single ions and single atoms, exploring new avenues completely. And there's a huge amount of excitement there that I would like to expand more about the reality bit and where we fit in that system. Talk about the Industrial Strategy Challenge Fund, supply chains, the importance of clusters, and this amazing global race that we have. So thank you very much for coming along to this discussion. Very briefly, Fraunhofer Centre for Applied Photonics. I have about 80 colleagues downstairs, staff and students, who are immersed in the world of photonics. So lasers and optical systems. And we embrace a wide range of applications. We're problem solvers that are making new lasers for sensing, measuring, imaging, communications, and computing. All similar words we hear in the world of quantum. So very briefly, we're on that journey from research to reality, whether that's making ray guns or things that look like ray guns to detect explosives at a distance, helping the local space industry with CubeSats, using mid-infrared lasers to check pharmaceuticals to make sure the right amount of ingredient in every tablet, or working in agri-tech, but also point as well to the processes, the tools and techniques to integrate photonics and miniaturize photonics, and that's a big part of the journey that we're on. So I think, and I also need to thank Dame Frances, not only for the amazing report, but for also beautifully putting in a nutshell that Fraunhofer is a Janus organisation. I've never been so pleased to be called two-faced. It's marvellous. It really does sum up the fact that we're here embedded in the research base in the university, but working so wholeheartedly with industry. And you put up a more sophisticated picture, and we'll come to that. Too often, the road from research to reality is oversimplified, and it sounds linear. And we do it ourselves. We point from things that are 1 metre long and a big optical bench in a lab, and how we prototype that, get down to a proof of concept, perhaps 30 centimetres, and we call this a product. And it is a product, and it is for sale, and it is quantum tech, and it is real. But there's a whole other journey to get from 6 centimetres down to something that might end up fitting inside your mobile phone. So I'd like to explore some of the demonstrators. So the Industrial Strategy Challenge Fund, along with the academic hubs, has been a big plank of why the UK has got the position it has already. We're showing here 3 demonstrations that we've done. For the more observant of you, recognising that building out the window, you realise this experiment was done just outside there, on the edge of the Technology and Innovation Centre. This was a quantum key distribution system where we're sending quantum keys from the top of the John Anderson building down to this building. We're doing that with British Telecom, but also with a wide range of very small, micro and medium-sized companies. This gargantuan piece of kit here is for position, navigation and timing, with British Aerospace Systems, who were the end user, if you like, of this wonderful demonstration, which also involved a lot of the smaller companies and local companies across the UK, to put cold atoms on a plane and fly it around to make sure the thing worked. This here is a hydrogen detection system, so measuring tiny amounts of hydrogen at tens of meters away. This demo here was for Sellafield and for nuclear storage purposes, but there's a new project now with British Petroleum, again involving much smaller companies to help detect hydrogen for the hydrogen economy. I call these demonstrators, some people would call them prototypes, but these are heroic demonstrations. These are the first off. This is getting the stuff out of the lab into the field. They are not made with off-the-shelf components. These are made up of heroic subsystems, made up of heroic components. We have a chicken and egg situation of trying to create a genuine quantum technologies manufacturing supply chain where the 1-2 person company down here doesn't know what to commit to make to get all the way through to the end user. That, for me, is where we are in a very, very exciting space, proving these things are possible, getting the attention of the multinationals and showing the potential so that investors can believe this really is coming, it can be demonstrated, but there's still a lot of work to make this smaller. So I've borrowed a diagram from the wonderful report, and I'm going to dumb it down a little bit in my own simple way. Working prototypes, we've seen some demonstrators there. There's a lot of work to do there from pre-production and pilot laboratory, but there's a whole extra stack of work to actually make that real-world manufacturing. For those of you in the audience who know nothing about quantum, imagine you've never seen a motor car and someone makes a prototype. They take away the horses from the carriage and they put a steam engine on it. They have made a prototype motor car. That's not fit to be manufactured. That's not what the end user needs. But we learn a lot along the way. So once you show this to someone, perhaps they'll decide they need a Land Rover. Maybe they're a farmer, they want to go off-road. Maybe they need something faster like an Aston Martin to drive around a racetrack. That informs the design decisions of what you're going to manufacture, but it has to come all the way back here. You need to redesign the chassis. You need to design an appropriate engine and a gearbox and the wheels and the tires and absolutely everything. This original prototype didn't have a windscreen. There's a whole industry out there of people making windscreens. So what's going to come as we develop these technologies and work out where the economic and social opportunities are for the UK? Still lots to be done. And it is a global race. 2025 will be the International Year of Quantum. Governments around the world are putting billions into this. We are not alone. There's another $2.5 billion that we're expecting to come in the next 10 years in the UK. And Dame Frances alluded to this. We need to see an appropriate plan for that. We need to see that rolled out. So everyone around the world would like their own quantum cluster. The Finns reckon theirs is unique. Other people might argue, maybe Denmark or Australia or Canada might argue. In Europe, the flagship wants Europe to be the quantum valley of the world. Well, here in Scotland, we don't call them valleys, we call them glens. So our glen of quantum entanglement we have reduced to glentanglement. Sir Jim hinted that we were building on a great base here of photonics companies. So with apologies to those who are writing quantum software and those who are involved in superconductors and cryogenics, there is a huge percentage of the quantum world is actually, we recognize as a photonic world. So we've been involved in quantum technologies for at least 10 years now, and we got some of the local companies involved very, very quickly and helped build some momentum in that cluster. So roundabout, we reckon it's more than 50% of the Innovate UK projects involve at least one Scottish partner. Fraunhofer ourselves, we reckon we're involved in about 30% of all the Innovate UK work in this. So we're in the right space, the oil in the machine of getting this stuff out there. But we're not doing it alone, and that's not to say that there is a vertical supply chain here in Scotland, far from it. This is really, really collaborative. So right back to photonics here. The Photonics Leadership Group produced these numbers that show there's various regions around the UK where there's very substantial employment and very substantial output and a very real growing, rapidly growing photonics sector, larger than pharmaceutical, larger than space, growing faster than both of those, but not often in the limelight because it lacks some of the larger companies. So the Scottish Photonics Cluster was clicked to get involved, and I had a little look at some data. I looked at the Innovate UK projects we've been involved in the last few years, photonics and quantum, but the numbers would look similar with photonics or quantum. When we win with Innovate UK, I have taken away the financial support to ourselves. This is the financial support that goes to our partners, whether they're in academia, large, small companies, etc. And you see that Scotland's doing very well. There's a lot of support and a lot of activity here, but it is, of course, spread across the UK very, very well. No great surprises there. Also, courtesy of the Photonics Leadership Group, if you look at the makeup of the photonics industry in the UK, I think this might tell us something as well. Similar to other sectors, whether you're looking at engineering or manufacturing or other physics-based sectors, there are very few large companies, but they dominate the turnover of the UK. And there's a very, very long tail of small and micro companies. But there's a fair number of medium companies. So I was a little bit surprised when I looked again at the Innovate UK awards. And you'll see here in the green, the total project costs, and the blue are the award costs, the finances drawn down by the organisations, split across the type of organisation. So my gut would have told me we did a lot of work with small micro companies indeed, and some large companies, end users, and yes, plenty of projects with our academic partners, many in the room today. But I think what's slightly surprising is the number of medium-sized companies being involved in these projects. And I think this points as well as to where some of the opportunity is for the UK, and it also shows the immaturity of the sector. So I think we're on an amazing journey of maturing all of these technologies. I hope we've played a part in getting the smaller companies to meet the larger companies when otherwise they might not be able to demonstrate what's actually possible. And then the next part has to be, along with the skills and the VC money, the opportunities for the smaller companies to scale up. And we know there's scale-up challenges in the UK, but I think there's a vacuum of the tier 2 companies that the multinationals normally buy their equipment from, because this is moving so quickly from physics lab through to the real world that there's really exciting opportunities for these small companies and micro companies to grow and dominate their sector and sell around the world. And one of the difficulties is we don't know quite what the engine or the gearbox is exactly supposed to look like yet. So we're back to Dame Francis and the iterations that we have in engineering and development, and there's a lot more to be done. So a few conclusions. Yes, it's a global race. It's incredibly exciting. Clusters and RTOs and universities can have enormous impact, and we've seen that with the academic hubs and the Industrial Strategy Challenge Fund. We don't do it in isolation. It is very, very collaborative in the UK. I think that has been our great advantage, is in introducing everyone to each other so we can have those conversations about what do you need, what can you make, what do you need, that goes round in circles. It's incredibly complex, and there's a lot more to do, but I do believe there's a huge, huge opportunity for growth for all of us. And the missions are coming up, and I do hope that we remember in the missions that we are still making heroic components and subsystems to try and make these systems. And there's still a lot of work to be done. especially in processes and integration and in infrastructure. Thank you very much.
Thank you, Simon. And now our final speaker before we go to Q&A is Rachel Mays. Rachel has spent over 15 years within UK government and Parliament developing and evaluating science and technology policy within the House of Lords, DEFRA's Chief Scientist's Office, the Government Office for Science, and within the Technology Strategy and Security team in DSIT. And most recently, she led the development of the UK Government's National Quantum Strategy. It's great to have Rachel here with us, and please welcome her to the screen. Thank you.
Thank you very much. And I'm really sorry that I can't be with you today in person. I was hoping to be, but for personal reasons was not able to. So I have the honour of summing up and really sort of setting the context for the Q&A session. So I'm just going to run through the sort of a lot of things that have already been talked about today in terms of the quantum programme activities, how we've got to where we are today, and some of the key things that we're planning to do within government over the coming months. So just wondering if my slides will come up on here or if I need to share them. But maybe I'll get talking anyway. Great, thank you. So in terms of the quantum programme, I think you've already heard an awful lot about it, so I'll try and skim over this bit just to save a bit of time. So the quantum programme's been going for about 10 years now. It comes to a close this year. And as we've already heard, over that period, we've spent about £1 billion across various activities from funding the quantum hubs, which bring together industry and academia around technology development, as well as doctoral training centre activities in quantum. We also have the Quantum for Fundamental Physics programme out of STFC. In terms of the quantum activity, the programme activities, as I've said, so we have activities across research, innovation. So you've heard about the Challenge programme, where we funded about 180 companies and around 180 million of funding to innovate through the projects that you've heard about from Simon. Alongside this, we have key bits of infrastructure, such as the National Quantum Computing Centre, which is due to open this year, which is really looking to help scale quantum computing and look at adoption and readiness within the programme. And you've heard a lot already about the National Physical Laboratory and their testing and assurance work through the National Metrology Laboratory and the doctoral training centres. And just to remind you, the quantum programme has been going now for a long time and has great partnerships across the people that make up the programme, which includes DSTL, NPL, DSIT, the MOD, GCHQ, and various parts of UKRI. So in terms of what has this achieved, actually the programme's had great successes so far, many of which you've heard about already. So we've first in Europe for world-leading research, and third globally for the quality and impact of research. We're also second in the world for the number of quantum companies, and also second in attracting private investment into the country. And as Simon has already alluded to, actually we're building on really broad industrial and academic capabilities across computing, communication, sensing, timing, imaging, and have a very vibrant supply chain in the UK. So we knew that the programme was coming to an end in 2024. So towards the end of 2022, we started to plan for the new quantum programme in government and across the partners, and really to start thinking about, what fits around the programme, recognising this global competition and growth that we were witnessing, and the need really to maintain that global position that we have in the UK. So the quantum programme, the quantum strategy is focused on a number of pillars, and it really builds on the success of the programme, but looks to then gap fill and thinking about scaling, as we've talked about today. So to really start to progress some of the challenges that we've been talking about. So the first pillar is just to continue to fund world-leading science and develop the skill set. The second one is around addressing these scale-up challenges and helping businesses to grow. And then the third one is around adoption and really creating that pull and focus on societal benefits. And then the last pillar really is on supporting innovation and the ethical use of quantum through international regulatory frameworks. I think what we've heard a lot about today is that there are many potential applications for quantum technologies. They aren't just one technology, they're a suite of technologies that have many benefits and opportunities, but that in itself represents a challenge. So what we try to focus on in government is making sure that we have clear trajectories towards areas of high impact. And as Francis mentioned, we did that through the development of 5 quantum missions. So towards the end of 2023, we published these missions, which were developed in collaboration with the community, and they focus on achieving key technological milestones, such as achieving scalable quantum computing or networked systems in the UK, as well as key application areas for sensing that Melissa's already touched on. So one around getting quantum sensors into the health system, one around position navigation and timing, and another around quantum sensors for critical national infrastructure. You may have already heard that government has its own missions. We are also looking at the value that quantum can bring to government's missions, be that economic growth, where we think that quantum will play a really important role, and government has signalled that it sort of sees the importance of quantum and will continue to support it moving forwards. But quantum also has value to the other government missions around an NHS fit for the future, taking back our streets, and building making Britain a clean energy superpower. So what have we focused on so far, and what are the challenges that we're going to face in the future? Just to sort of set the context a bit more, as Francis mentioned, we have committed to funding 5 new hubs that actually fit very well with the quantum missions. So 2 of which are in Scotland. So we have the Quantum Networks Hub, position navigation timing in Edinburgh and Glasgow. Then we have sensing, imaging and timing in Birmingham, biomedical sensing in London, and quantum computing in Oxford. And as with the last set of hubs, these will be really partnerships delivering a programme of work across a number of leading academic institutions across the UK. We've also established 5 new doctoral training centres and run competitions around networking and PNT, as well as European projects. And the National Quantum Computing Centre, which is due to open shortly, has established its testbed programme, which will enable access to 7 different quantum computing platforms, and they already have an extensive Spark programme. So just looking ahead to the future, as you can imagine, we are in the midst of a spending review. So this is a big challenge that we are currently trying to navigate, and that is looking at, what does 1 year versus multi-year spending activity look like for quantum. And we are also in the middle of really thinking about the next steps for the infrastructure review. So the Royal Academy of Engineering produced a very helpful report. As Francis said, it's really the start of the conversation, and we'll be doing community engagement just to better understand the crossover of those requirements for infrastructure across quantum, but also how it marries to semiconductor, telecoms, AI or other critical technologies. So we are in the process of doing that internally in government. and we'll be coming out and doing community engagement to just do deeper dives into specific strategic application areas. We're also due to receive the Skills Task Forces report in the near future, and that really has been over a year's worth of work with a lot of people within the community who have started to really get to grips with the skills needs beyond PhD, as we've talked about today. So what are the technical skills we need? How do we bring in skills from other sectors? How do we upskill and transfer people across? So we will be really using those evidence bases to build our activities within the spending review. Given the time, I will probably stop there instead of going through a number of other things and just pick things up in the discussion.
We can sit up here now. Rachel, thank you very much, and sorry for that technical glitch, but I think you covered all the major points. I'm going to invite Simon and Francis to join me here at the table. Of course. Gavin has said we're okay till 7:30 tonight, so I'm sure those in the audience will be delighted about that. We'll bring in fish suppers to keep you all sustained. But Rachel, thank you very much, and hopefully Melissa is still here as well. Yep, we certainly hope so. But with that, colleagues, Gavin will help us curate any questions that may have come in online. But we have 25 minutes, half hour or so for us to open up to the audience. If you keep your points succinct, please, and if you want to start, then introduce yourself, just what your affiliation is, and then point your questions either directly to individual speakers or make the point, and I'm sure that'll be picked up, and I'll try and keep that moving. So with that, colleagues, Q&A starts. Let me open the questions to the audience, please. Please.
Francis, you mentioned
if you introduce yourself, Michael.
I'm Michael Kelly, University of Cambridge, retired. But you mentioned the word manufacturability. Could you give me any indication from your review about what fraction of total effort in the quantum technologies program is dedicated to this specifically? I'll indulge myself for 1 second, a minute, to say that in 1988, I took a device from the Hearst Research Lab to the Marconi people based on a single quantum tunneling barrier as an alternative Schottky diode. And they said, this is great, we want it for all these reasons. But it took 25 years to develop and redevelop the whole MBE growth system to actually make wafers that had 1% standard deviation across the wafer and wafer to wafer, because the first time I tried it was 300%, and after 15 years it was still 30% standard deviation. So to get down to 1%. So the question is, how much effort is made on the manufacturability of some of these things?
Right, okay, I think the truth is not as much as needs to be. And right now, I think, as Simon said, a lot of the demonstrations have been kind of heroic one-offs or a few-off. I think going forward, the plan with the next generation of hubs is that there should be more engagement with that whole issue of how do we miniaturize things and how do we make them more manufacturable. But up until now, it's really been much more, does this work at all? What we need to do next is, as I was saying, is make sure there's enough emphasis within the next generation of activities looking at the real pull-through into manufacturing. But I can't give you a figure at the moment because I don't know the overall figures for each of the hubs.
Simon, would you like to comment on the manufacturing challenge that everyone's facing?
Thanks. I wouldn't put an exact number on it, but with $1 billion going into quantum tech in the UK, I would certainly say less than 100 million because of the maturity level that's there. There have been a couple of fairly significant Innovate UK projects, QT Assemble and Upscale, were projects purely looking at the processing and assembly of the components to start chipping away at the manufacturing challenges of integrating different materials and getting them packaged down to show that miniaturization was possible. So there have been some successful projects in that direction, but still a lot more to be done to get to the sort of genuine industrial scale, repeatability, mass manufacture that you're alluding to.
Can I also add? I mean, I think that often you think about a rule of thumb, don't you, in terms of at least factors of 10 between something at research into a sort of an R&D and maybe a factor of 100 into manufacturability. And we're not seeing that kind of level of investment in the manufacturability as yet.
Melissa or Rachel, I don't know if you want to add anything before we go to the next question.
Rachel, I don't want to interfere you, Rachel.
Thanks. So I'll just really quick point. I think that's a very fair assessment. So we don't track things by those sort of categories, unfortunately. But I think Simon's probably right in terms of if you look at the focus of the programme over that time, in the first and second phase, we're sort of now shifting much more towards scale up. So we need to make sure we design the next phase of the programme to bring in much more opportunity to do those sorts of activities.
Thank you. Please go ahead, Melissa.
Yeah, I was just going to say, actually, I think it's interesting to pick up the point that people were saying, we're talking about quantum technologies, and I think the tolerances are different across them. And I think it's a very nice. So I work on atomic defects in diamond, and I always say mine are the reject diamonds that the people in quantum computing or entanglement don't want. So, for example, the tolerances that the diamond defects that I could work with, having ensembles of these defects, will be perfectly fine for me. But if someone was wanting to use it in quantum comms, which people have done, and entangled the qubits, then they would want very isolated qubits. So I think it's actually a very nice ecosystem. I often say, I can work with the broken biscuits, and there's a market for the broken biscuits, but there's also a market for the pristine biscuits. So I think the manufacturing challenge is nice in that we can embrace all levels or capabilities, I guess, in that regard.
Thank you. We've got another question here. Who's looking after the microphone? Just at the front, please. If you can introduce yourself, that would be great.
So it's Derek Reed from Heriot-Watt University. So we've heard from a couple of speakers about the supply chain gaps in quantum technology, and I'm interested to understand from the panel, what's your perception on the gaps in terms of foundry services for integrated photonics, some of the materials that are needed in the quantum supply chain?
Anyone like to pick that up to start?
I think that one starts with Dame Francis and her report on future foundries.
Yeah, I think that I think one of the challenges and one of the risks we have is that people think because we do have some foundries in some areas of compound semiconductors and so on, that actually we've got a capability. But what we need to be thinking about is what are the requirements really for quantum? And where do those align with the capabilities we currently have, and where actually is there a divergence? And I suspect at the moment there's quite a divergence, but I'm not going to claim to be an expert to look at all the different aspects of foundries. But we need to ask exactly that question. Are the capabilities good enough? Where are the gaps?
Thank you. Simon.
I'm not an expert in this, Derek, as you know, so I'm not going to say specifically what we've got and what we're missing. But if we're looking at future investments in infrastructure and what we're doing, we have to remember as well this is a national security question. This was the big origin of quantum technologies with Sir Peter Knight and the DSTL labs. We're not going to do everything that's vertically integrated, and if we're going to pick winners out of the infrastructure review, it has to be something that the UK can support at scale, at a sensible scale, and enduring. It has to be a long-term commitment to whatever it is, and then we'd have to then balance that with what we thought our geopolitical relationships were. Are we going to trust that TMSC setting up in Texas? Are we going to use IMEC in Belgium? Or where are we going to go as trusted partners for the things that we can't afford for ourselves? So there's a wide range of capability in the UK in different areas, but in a rounded view of what the UK needs in quantum technologies, then we have to. So far, we've not picked a winner, we've picked a race. We've decided we're in quantum tech. And now it's going to boil down to what specific technologies we have to have in the UK. I don't actually know the answer to that.
So online, I mean, Derek also raised the question about Foundry's availability and where that fits into that quantum journey. Melissa or Rachel, anything you want to add?
I can add something to this, and I think it's become more apparent to me working with Rachel's office and the Government Office for Science is that we need to consider value chains, not just supply chains. So I think one thing is we still at this point, I don't think, have defined where the highest prize is, if you like, in the value chain, you know, and I mean economically and for security purposes. So whilst I think there's agreement that foundries are going to be a requirement, I think a consideration is as I think has been just raised now, is, you know, where is this very high in the value chain for the UK, both in terms of prosperity and security? That's all I would say, is I would just think about the terminology or consideration of value chain alongside supply chain. I again don't have an answer, because I realise this is a very big topic point.
Rachel?
Yeah, I can have a go. So I think it's a very valid question, and it's one we would love to know the detailed answer to. I think, as Melissa said, I think the challenge we have, you know, in the quantum team is we're looking at this from a quantum perspective, but actually quite often you need to look at it across a number of different areas. And I think even within quantum, you're looking at a set of different technologies and applications. So for some, they're nearer to markets and others are further away. And I feel like, having worked on quantum for a number of years now, I feel like even in the last year, things have moved on like massively, and companies are now getting towards really understanding their own needs in this space. But it's taken a while to kind of get to that point. So it feels like now is the right time to really have a go at answering that question, which is why we're kind of doing more deeper dives. But you're talking about the needs of a number of applications across a number of technology areas. So it's quite hard to get to a sort of a definitive answer. I think we feel like we know the key opportunity areas, but I can't claim to know the specific points that we've just been talking about today.
Thanks, Derek. Very pertinent question. Thank you. We'll maybe take input from the online.
Sure. So thanks very much. There's quite a lot of great questions and comments online. One comment just to start with, which is no one's mentioned systems engineering, but they really should. So I'll just mention that now. Various questions. Shall I give you a couple of questions?
Please,
a couple of questions from online.
And you'll attribute them as well, Gavin. Yeah?
Right. So one is attributed to Chris Dungley from the High Value Manufacture Catapult, who asks investment priorities. How do we prioritise public investment? For example, has a UK make versus buy QT assessment been undertaken? And then there's one which attributed to Anonymous, apologies for that, which is how do technologies such as additive manufacture and heterogeneous integration play into the acceleration of manufacturability of QTech, and how do we support that?
Francis, we've been taking advantage of you being on my left-hand side. Would you like to touch on those? Chris Dungy, by the way, is the CTO, HVMC. There, you're there. Chris's twin. Would you like to elaborate on your question?
Yeah, sure. Thank you, Sir Jim. Yeah, apologies. I misinterpreted the rules of the game at the beginning. So there you go. Yeah, so I'm Chris Dungy, the CTO for the High Value Manufacturing Catapult. Nice to meet you all today. We're in our infancy in terms of really exploring this space. So that's why myself and my colleague Rab Scott's in the room today. So we had a couple of questions, particularly around investment priorities. So how do we prioritise public investment? For example, has a UK make versus buy assessment been undertaken? And if so, what does it tell us about future prioritisation?
Yeah, thanks. I think really it's to some extent what Simon was saying previously. There are a number of factors you might take into account when looking at a make versus buy, which includes things like the strategic positioning. Is this something that we need to have control over for defence and security purposes, freedom to operate and so on? To what extent do we think we're any good at it? So we're starting from a strong base. Synergies, perhaps, between quantum and other areas where we've got already an existing capability, so we have something to build on. So there are a number of different factors, and I think the truth at the moment is I don't think we've made those decisions, and that's part of the conversation that needs to be had now, because we do need to focus in on one or two things that we think really would be the things that we would offer. And this is important also for international collaboration. People think you can sort of get access to other people's technology through international collaboration. You can, but only if you have something on the table to offer that they value. So we also need to think about what are the gaps in other people's capabilities, and are those some of the things that we might actually say, okay, this is our contribution to the trade, if you like. So it's a very complex thing to do, but it needs to be done.
Rachel, we're moving into policy and strategy here. I don't know if you want to touch on that with regard to the overall UK position just now.
Yes, so I think I'm at the risk of being a broken record, probably will repeat my last point. So I agree that's where we need to get to, but I think we're talking about quite a nascent sector. So it's quite a hard question to answer when you're really talking about, as Simon said, quite often companies that have recently spun out of universities, you know, and people really trying to understand their own value proposition for what they're developing. So I think, you know, I really do feel like the picture is emerging, and we're starting to see some clear opportunities that do overlap with other priority areas across government. But I'm reluctant to kind of put those down now, because we're just in that process of really thrashing out, you know, for what purpose, what's the demand. So you know, the quantum sector is not massive, so you really do have to look at that demand from industry alongside demand for other industries to make quite big, significant infrastructure plays in the UK. So I think I sort of support what Francis was saying. You know, there's a wider point here about the need to make sure that our infrastructure overall is of the right, you know, standard. But then there are some specific plays where we need to just look at the requirements for those pieces of infrastructure across different technology areas and industries to probably get to the answer. I don't think it's necessarily a quantum answer.
Okay, Gavin will remind me what that second question was, just on the manufacturing piece. But Simon or Melissa, do you want to add anything to Chris's question?
I can add additively. One thing I think to follow on from the previous question and this most current question is actually there's situations, and I think it will increasingly be the case, where the IP or the you know, the main value in the proposition lies in actually the manufacturing. So I know with Circa Magnetics, there's IP tied up in that helmet that the child sort of wears, and that's additively manufactured. I know for the work I'm doing, we're looking at, you know, additive manufacturing for integration of our sensors. And so I think there's situations where actually the commercial value lies actually in this advanced manufacturing. I know it's not going to be across all of the technologies, but I think this is where, you know, IP is held, is all I would say to that. But yeah, pass on to Simon and others. Or
you can pass and we can go to another question.
No, I'll happily jump in there. I think it's a very difficult question, Chris. It's a very good question. We are at that stage where we have got people up and down the supply chain saying, what do you need? What can you make? To try and work out what the winning products will be. I should also say, I know I've got a very broad audience here. There are quantum tech products on the market. It's real, and they sell. You can buy a quantum key distribution system. We saw some nice examples on the screen. So, but there's still a lot to work its way out. So I don't think even today we could absolutely put our finger on what the UK is completely lacking. So as I think as things boil down, and when we say it's a national security question, again, if it's a broad audience and you've not heard these things before, we're incredibly reliant on GPS these days. And we've seen countries shoot down satellites. If GPS was denied, that has a huge impact on the UK economy and economies around the world. If we can develop quantum position navigation and timing systems, we're not utterly reliant on the GPS that guides our emergency services and coordinates the timing of banking transactions, as well as delivering your shopping at the weekend. So there's that level of things. And in quantum computing, if we're able to, if other countries were able to hack the internet as successfully as is predicted, it would be an end to financial transactions across the internet, which would totally change what we're doing. So until such times as we can bottom out what everyone needs, and then where do those components come from, and where do those materials come from, and then which countries are those foundries in? Are we comfortable with a long-term supply chain from particular countries? There's still a lot to work out.
Gavin, I didn't want to lose the other question, if possible.
And so it was how do technologies such as additive manufacturing and heterogeneous integration.
Yeah, okay. Yeah, so we've touched on that to some extent on that.
Yeah.
So hopefully those that posed the question are happy with that answer. If not, I'm sure they'll come back. Anything else in the room, colleagues? Yes, please. Just down at the front.
Thank you. Good afternoon, I'm Evelyn Thoma. I'm the Director of Strategy for the JWNC at the University of Glasgow, so we're a nanofabrication facility. I suppose my question is a practical one, and it's that of timing. So, Rachel, you talked about, at the moment, you're looking about the intersection between some of the different strategies and policies that have been looked at. In particular, I think there's massive overlap between what came out of the quantum infrastructure review and what came out of the semiconductor infrastructure review. And I think as a small company, we should be, a small country, we should be making sure that we're really looking for all of those commonalities to help us make those decisions. I suppose it's just about timing. There's a lot of complex questions that were highlighted there that we need to answer. And as we've said, the rest of the world isn't standing still. It's moving very quickly. They've got their investment programs in both quantum and semiconductors. So what timescales do we reckon we're working to make some of these decisions?
Right, Rachel, I am looking at you, but I suspect I know that we might get a very well-informed holding response. But would you like to react?
Yes, yeah. I mean, you're absolutely right. So we haven't had the sort of start date fired yet on the multi-year SR, but to me that is the sort of crucial time period to kind of have made some of these key decisions. Like we will not be able to make all the key decisions for the quantum sector in the spending review. I think it's probably worth having that in mind. So the way that I would approach it would be, what are the no regrets, as you said, you know, the wins that are of value to a number of sectors that we can make now, we should be making for the spending review, but some of this will take a while to get to the right answer. I think for the UK, I think you're right. There are, you know, a number of activities from different countries who have made significant plays on pilot lines or fabrication, for example. But I think for the UK context, I think we are where we are in terms of the spending review and the sector. So let's try and make sure we get through what we think is most important now, and we will be doing community engagement to make sure that's informed by the community. But yes, no, it is a holding response, I'm afraid. So a work in progress, I think, but good question. Colleagues, anything else in the room, please? Or online, Gavin?
Yeah, there's a couple. So there's one question here from, I just checked, is Rachel Oliver here? No. Okay. Or I do that again. So Rachel Oliver says, are we seeing sufficient integration between different strands of government strategy? And she's saying particularly on semiconductors, photonics and quantum. Right, we're back actually to systems engineering and government, quite frankly, in terms of multi-departmental collaboration. But I will leave that open to volunteers to pick that question up.
Certainly. If you'd all like to put your hands up now, is there anyone in the room who would like to see an industrial strategy that lasts at least 10 years that fully integrates photonics, space, defence, compound semiconductors, etc.? Yes, please. We're looking at companies making, companies write their business plans. They write them on timescales well beyond what we typically see in a government spending review. The boldness to invest $1 billion in quantum technologies was a serious market intervention, a recognition that the UK had strengths in optics, photonics, and these technologies that were going somewhere. That was tremendous to have that bold early vision and show leadership ahead of the level of risk a VC would invest in. And we're now seeing VCs investing substantially, which partly answers Evelyn's question about timing and Michael's question about manufacturability. Yeah, there are some who are pushing the accelerator as fast as they can because they want to capitalise on that opportunity. As for the rest of us who are going across the community from research to early demonstrators and prototypes, yeah, we'd love to see an industrial strategy that was seriously long-term, seriously committed to, and joined everything up that Professor Oliver suggested. Yeah.
Cool. Is there any other input at that?
Maybe I can save Rachel Mays here from taking another government pointer. I can give some perspective from the Government Office for Science, and mindful a real mission of that is putting excellent science advice at the heart of decision making. Of course, you can't make the decision, but can and I think something that the Government Office for Science is doing is looking at rolling out I guess strategies that look at challenges at a granular level. So what we've done is we've worked with Rachel's office looking at across quantum sensing and looked at taking, this so-called deep dive at what are the cross-cutting technologies and capabilities. Not just saying we need lasers, but saying we need, mid-infrared lasers of high power, for example. And the same thing's being rolled out with the future communications team, and the plan is to do it next on semiconductors. So I can't say that there's going to be an industrial strategy, but I can say that certainly we're looking at sort of this granular level at areas of commonality, areas of strength, and areas of opportunity. So I think that's an activity Government Office for Science is doing, and I guess then that feeds into advice, which I appreciate. The next step is recommendations and policy, so it is a precursor to that, but I can sort of say that's certainly an aspiration of giving evidence and advice on that level.
Okay, colleagues. Gavin, anything else you want to raise online? Or anything else in the room, colleagues? We're coming to the last question or two. Right, Chris, you've I'll just double check online anything. I will come back to you, Chris.
So there's one more question online from Seb Wilkes, who asked, for those entities using quantum sensors in application, is there enough push to ensure that they use or support British quantum sensors versus from abroad?
Okay. This is sort of local, national content as we build quantum devices and systems.
Yeah. Well, I mean, as we've been saying, a lot of these quantum sensors we're getting at the moment are kind of heroic push from the university sectors together with small companies. So those are the ones that we're following the exploitation of. And yes, those will have been primarily made or assembled in the UK. So actually we're getting some of that experience. And if you look at something like Ouija, that really is something which is, developed in the UK, made in the UK, and is now being assembled in the UK and taken out and put on volcanoes in Sicily.
And supported by
UKRI.
UKRI, yeah.
I think it's an important question. I talked earlier about some of our Innovate UK projects. We also have projects directly with friendly Five Eyes countries and direct industrial contracts that we don't say too much about, but those customers are asking us questions about where our supply chain is and are things coming from the UK. So I can only imagine that their customers are perhaps people like MOD or National Quantum Computing Centre, that they want to know that they've got that supply chain. So it's a hot topic, and it's bubbling away in the background for sure.
We've got one more question before I go back to Chris. One just at the front here, please.
I'm Anke from Anke's Inn. Just commenting on the sensors. I did a study recently for Germany about quantum sensors globally, and the UK is second. on that list, behind the US, of course the US has much more, I think there will be sensors from the UK that will be used in the UK, but also globally.
Yeah, that's very helpful. Chris, but we'll just get the microphone so that our colleagues online can hear the question.
Thank you. I'll be brief as I can. I appreciate the time. So Dame Frances had a brilliant slide that showed one of the key challenges in that scale-up mid-TRL space. I'm just going to pose a question. Do we believe that we need a catapult-like entity to support and facilitate and work with the hubs in that environment?
Frances.
Thank you. I'm not sure I would necessarily say a catapult-like entity, but I think there is value in some kind of organisation that's, is one of these Janus organisations that can help translate between the industry needs and the what academia can make now. How you actually organise that and where it should sit, I think, needs a bit more debate. But I do think there's a bit of a gap sometimes between the academic community. Not that they can't do it, but actually it's not what they're best at. And I think we want to find some people who are really good at doing that translational work and taking what we often heard when we were doing this review as a proper problem-solving approach, where you very rarely get an instantaneous match between technology push and applications pull. You need to do some compromises, you need to do that iteration. And it's not necessarily what universities are good at. But that's just my opinion.
No, and we'll conclude. I mean, I don't have the answer either, Chris, but I would say sometimes the gap can be filled by connecting those things that are already there, like the compound semiconductor catapult, the high-value manufacturing catapult, Fraunhofer, and other bits around the system. So sometimes if we take that systems perspective, rather than have these individual components, actually connecting them in more innovative ways is likely to give you the multiplier without spending very substantial sums of money creating something new, when actually you can create programs where the existing infrastructure can feed into it. The James Watt Nanofabrication Centre, for example. There's lots of components in the ecosystem. Connecting them better might be part of the solution.
So it might be more of a programme than another entity, a programme that helps support that. And I think the other thing, when we did this review, there were people going, let's invent another catapult. Yeah. And then you think, where are the skills going to come from? We know we're a bit poor on skills and of people who have the competence to work in that at the moment. You want more technicians who are able to work in that space, whereas actually we've probably got some of those already in our existing infrastructure. And we just need to kind of teach them about quantum.
Yeah, Good question, Chris. Catapult's an example of a research and technology organisation, as we both know, partly inspired by the Fraunhofer model in Germany. The UK developed its catapults, but across the RTO space, you've got other organisations in the UK, NPL, doing what they're very good at, compound semiconductor applications catapult, looking more at the packaging of photonics technologies. We've got the James Watt Nanofabrication Centre across the city there. Yep.
Yeah.
Absolutely. So that's an innovative mechanism Glasgow University uses, and the National Compound Semiconductor Centre in Sheffield. There's lots of parts of the puzzle. So I would argue squarely that there are RTOs already doing quantum and doing it very well. I don't think the landscape's ever complete, but we should always make sure that what we do makes good use of taxpayer money and is complementary to the things that are already there.
Just as we close, Rachel or Melissa, any final inputs from you before I close the session, please?
I guess I could just say a similar thing. I think actually what would be really useful is like a community of practice. So I think we have these entities, as has been said, and the know-how, and I think there would be a lot to be gained by having I guess a resource or in which like matchmaking, if you like, or a directory where you could look up and people are part of this community. And I think another resource that I think helps fill that or jump through that gap that Frances very nicely showed on that slide, is actually having test beds or access to real life or as near to facilities where you can demonstrate and get your pilot data and test your prototypes. And I think, again, that would probably be not just a single place, because you might have a civil engineering application or you might have a medical application or something like that. So I think the key message for me is that the UK quantum ecosystem is very rich. I think the step would be just how we can have it more connected and integrated and have a, champion the spirit of openness and collaboration is what I would say, rather than some standalone entity.
Rachel, maybe a concluding remark which we might be tidy around the national quantum strategy. Over to you.
Thanks. I think I would support all of that. So when we've looked at the catapult question in the past, that's the conclusion we've drawn, is there are already a lot of great capabilities in the existing landscape. So we want to build and connect those. So yes, I guess just a final sort of thank you for helping us get this far and developing and delivering the strategy. And please do engage as we reach out to do these deeper dive sessions on sort of specific requirements going forwards. So yeah, just a plea for that. Thank you.
Thank you very much. So with that, colleagues, I will bring us to a close. You'll allow me on behalf of FST to again reiterate our thanks to the Royal Academy of Engineering for the support for staging today's event. And I'm sure you'll agree with me that our excellent speakers today addressed a very challenging issue, but lots of opportunity. But we've heard through some of the answers naturally. There are big questions that have been posed, that there are answers still to be sought, but today is a helpful reflection on what those might be. So please join me in thanking Francis, Melissa, Simon and Rachel for their contributions. And with that, colleagues, the session is over, and those in the room are welcome to a networking session next door. And those online, thanks for joining us.